Okay, so we're still trying to find zeros of polynomials. We're still going to go back to synthetic division. But in the last section, it told us what, a number to try, or two, so that we could get things nailed down. This helps us, this section is about how to kind of find the zeros if you don't know anything. So there are two different kind of tools that you have. One is Descartes' rule of signs. Descartes' rule of signs says, oh, that was weird. You just count the number of sign changes over the polynomial. Oh, I want to make this, get some more things going here. And if you just look at f of x, so this is positive, a positive coefficient, that's positive, that's negative, so that's one change. And then that's still negative, and then that's positive, so that's another change. So you have possibly two positive real roots. And then if I plug in negative x, so the x to the fifth will become negative because negative x taken to the fifth is negative x to the fifth, so that'll be negative 4x to the fifth. The x to the fourth will stay the same because an even power cancels out the negative. Same with x squared, so that stays the same. Minus 2x will become positive 2x because it's minus 2 times minus x. And then plus 7 stays the same. So I start out negative, then I go to positive, that's a change. Go to negative, that's a change. Go to positive, that's a change. Stay positive, that's also a change. Oh, that's not a change, sorry. So 3 possible negative real roots. So remember that we could have an a plus bi. We could have a complex root. Those come in pairs. So if I don't have two real roots, then I have none because I lose a whole pair. If I don't have three negative real roots, then I have one because I would lose a pair, and then you can't lose a pair from one. So I either have three or one. So in this case, we know for a fact we have one negative real root. So we could go hunting for that one first. The probably more useful tool is called the rational roots theorem. So if I have f of x equal to 5x to the 7th minus 8x to the 6th plus 9x cubed plus 4x minus 9, say, then if it, by the way, if it didn't end in a number, if it ended with a multiple of x, you would factor out that many x's because that you'd have that many everywhere. So you'd factor that out, and then you'd look at the polynomial that you have left after you take it out. So you look at the constant number and the leading coefficient. You take all factors of this one divided by all factors of this one. So on the top, we would have plus or minus 1, plus or minus 3, plus or minus 9. Those are all the factors of 9. 5, we have plus or minus 1, plus or minus 5. So my possible roots are plus or minus 1, possible rational roots, sorry. So we could still have irrational roots. These are all the possible rational roots. So if I look at the divide by 1 version, then I just get all of these. But then because I could also divide by 5, I have plus or minus 1/5, plus or minus 3/5, plus or minus 9/5. And then I take those and try synthetic division to try to locate some of them. In this case, because it's a 7th degree, if I wanted to get it down to quadratic, which is usually the goal, I'd have to find 5 of these. Now, if you find that 1 is a 0, it doesn't mean it's not a 0 again. Once you have, well, let's just try this and we'll get to this. Once you have taken 1 out, you'll have a new polynomial at the bottom, and if it changed the 9 or the 5, then you can delete some of these options because they no longer exist after you factor that thing out. Okay, so number one, we want to select all the possible rational zeros. So I need to have in this case, my leading coefficient is 1. So in the denominator, I just have plus or minus 1. So that's not actually even interesting. If I do, so once I have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6 up here, if I take positive 1 over positive 1, it's the same as negative 1 over negative 1. Positive 1 over negative 1 is the same as negative 1 over positive 1, so I don't actually need to deal with the negative in the bottom, which I didn't before. So we just have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. These are our possibles. So plus or minus 1, plus or minus 6, plus or minus 3, plus or minus 2. Now going to the next problem, we're asked to find the zeros. And we want them in exact form, so don't plug them in and put a decimal approximation. That's what that means. Because, okay, sorry, my DVR just suddenly unpaused and came on. So this one is a quadratic form. You can list out the rational possibilities. The rational possibilities are plus or minus 1, plus or minus 19, because this still has a leading term of 1. But none of these will actually work because this doesn't have rational solutions. It does have some real solutions. But so if you try these and you get none of them are zeros, then you need to look at it again, because if you're given the problem, there should be some tool in your belt to solve it. This one, you've got something squared and something to the fourth, so this one squared, so you're going to do a substitution like this. So now we can rewrite it as u squared minus 18u minus 19. Things that multiply together to give negative 19 are 1 and negative 19, or negative 1 and 19. And the one that makes negative 18 is this one. So we're going to have u plus 1, u minus 19, and then we put back in, or not, x squared plus 1, x squared minus 19. This one doesn't factor over the reals because of the plus 1. So x squared for any real number is at least 0. You add 1, it's at least 1. So it's never 0. This one does. So at this stage, you can factor this one like this. Or in both cases, you could say, okay, well, I've only got a binomial now, so I'm going to go ahead and set it equal to 0. Then x squared equals negative 1, x squared equals, oh sorry, I got ahead of myself here, minus 19 equals 0 equals 19. And then from these, the thing which, when squared, you get negative 1 is I, but it's actually plus or minus I. If you do minus I times minus I, then the minuses still cancel, so you get plus I squared is negative 1. Okay, so this is plus or minus I. This one gives you plus or minus root 19. So these are all of our zeros. So it's x minus I, x plus I, x minus root 19, x plus root 19. The question asked for the zeros, not for the factorization. So we're going to put I, negative I, square root of 19, negative square root of 19. Oops. Negative. Geez, that kind of turned into a beating. Be careful putting an equal sign. And now 19, we want to write a polynomial that satisfies these conditions. Of lowest degree means don't add any extra zeros that aren't necessary. So we have real coefficients and a 0 of 9 minus 4i. That means we also have a 0 of 9 plus 4i. I can't have one without the other. If this one has multiplicity 1, this one has multiplicity 1. And it has a 0 of 0 with multiplicity 5. So that's multiplicity 1 as well. Okay, so we have x minus 9 minus 4i and x minus 9 plus 4i, and then x minus 0 5 times. So this equals, this part's just x to the 5th, and then we have x squared minus 9 plus 4i times x minus 9 minus 4i times x plus, running out of room here, 9 minus 4i times 9 plus 4i equals x to the 5th times x squared, so minus 9x minus 4ix, and then plus 4ix, so those two cancel, and then minus another 9x. If you have paper, so you can write all those steps out, just distribute the x in these two. And then plus, and then I have another foiling, so 9 times 9 is 81, minus 4i times 9 plus 4i times 9, minus 16i squared, so 4i times 4i. So x to the 5th times x squared minus 18x plus 81. I squared is negative 1, so that becomes plus 16. So x to the 7th minus 18x times x to the 5th plus 81 plus 16 is plus 97, x to the 5th. Okay, so a lower bound for the real zeros is it means that it is below all of the zeros. We have another theorem that I forgot was in this section. So there may actually be two. There may be an intermediate value theorem, but so upper and lower bound, the theorem is that if when I divide out x minus c, so I take the thing and I divide out x minus c, which would mean synthetic division wise that I take out c right here. If what I end up with here is all positive, then c is an upper bound for the zeros. That means it is bigger than all the zeros, so I don't have to look at any numbers, bigger than this one. So when you're using the rational roots theorem, if you use a number and these are all positive, then any numbers bigger than this one you can cross out. If when I take this out, these alternate in sign, plus minus, plus minus, plus minus kind of thing, then it's a lower bound. The lower bound means there aren't any zeros lower than that one. So then you can toss out any of the values that were less than that. This question is just telling us that -1 is lower than all the real zeros. But there's no reason that I can see to believe that 0 is also lower than all of them, because you could have some, negative a half. And -1 is still a lower bound for that. Okay, so the intermediate value theorem says basically polynomials are continuous. So if, for example, on this polynomial, I found a value that was down here. Let's say at 1 it was negative, and then at 4 it was positive. We don't know what happens in between exactly. We do know, however, that we crossed over the axis at some point. Whatever continuous path you make, well, that doesn't really look like a polynomial so much. Could be, though. Whatever continuous path you took, there was a 0 in there. So there existed a 0 between 1 and 4. So if one of them's negative and another one's positive, then there's a 0 between them, somewhere, intermediate being between. So 2x squared plus x minus 2, we want to show that there's a 0 between 0 and 1. So the way we apply the theorem is plug in 0, and we get -2. So it's a negative number. If you plug in 0, you just get the y-intercept. So -2 is negative. F of 1 is 2 plus 1 minus 2 is 1. So that's positive. So since they have opposite signs, there had to be a 0 in between. If they have the same signs, we don't know that there's not a 0 in between. There could have been 2 as you passed through. So if they're both negative, it still could have done this. But, or even, I guess, that and had 1 0. But at any rate, if they're on the other side from each other, then you had to pass through. So the function must have a real 0 on that interval. So we want to find the zeros. Because this is quadratic, we could use the quadratic formula. We can try to factor, but the thing that we need to factor then is -4. So our options are 2 and -2, 1 and -4, and -1 and 4. None of these have a difference of 1, so we can't factor it. So x equals -1 plus or minus the square root of 1 squared minus 4 times 2 times -2 over 2 times 2. So 4 times 2 is 8, times 2 is 16, root 17 over 4. Okay, so this one we want to factor over all real numbers. It's to the fourth. There aren't 4 pieces. We can't really group it. So let's just go trying to find zeros. Once we get down to squared, we can use the quadratic formula. So our possibilities for rational is 1, negative 1, 2, negative 2, 4, negative 4, 8, negative 8, because it has to be factors of 8 divided by factors of 1, so we don't get any extra there. Well, I guess not. Okay, so let's try 1. 1 for the x to the 4th, minus 3, 6, minus 12, 8. I'm not missing any, so I don't have to put in zeros. Okay, so the first one we're trying is 1. Bring down the 1. 1 times 1 is 1. Plus negative 3 is negative 2. Times 1 is negative 2. Add those and we get 4. 4 times 1 is 4. Minus 12 is minus 8. Minus 8 times 1, that's 0. So we have found 1. So 1 is a 0. Okay, previously I did something odd and I left this 0 here, so I've kind of redrawn this all. Once this was a remainder, so the polynomial I'm left with is this. So then I try again with 1. I take 1 out, because it could be a 0 80 times, well, at most 4, but the multiplicity we don't know. So we would try 1 again. Bring down the 1, times 1, negative 2, negative 2, that's 2, 2, negative 6. So 1 does not work again. So now I can say I'm through with 1. Okay. And actually, right now I have alternating signs. So that actually means that 1 is a lower bound for the zeros of this one. So remember, if you get all positive, then that means it's an upper bound. If you get alternating, it means it's a lower bound. So at this stage, let me grab this. This is the polynomial we're working with now. We've already got 1, x minus 1 out of there. So now we're working with these. But because I still have 8 on the outside, 8 here, 1 here, I don't get to lose any of those, except I do get to lose everything less than 1, because 1 is now a lower bound. So I get to cross out all these. So now I just have these 3. So we'll try 2. Bring down the 1. 1 times 2 is 2. That's 0. 0 times 2 is 0. So 4. 4 times 2 is 8. 0. So now we know that 2 is also a 0. And now I'm left with a quadratic. So this is x squared plus 0x plus 4. So far, putting this information together, I know that f of x equals x minus 1, x minus 2, x squared plus 4. The question asked the factorization over the set of real numbers. So these two are over real. This one, if I factor it, because it's x squared plus 4, so let's say that we tried to factor it either this way or using the quadratic formula, you're going to get the same thing no matter what. This is x equals plus or minus the square root of negative 4 is plus or minus 2i. So that's not over the reals. The factorization over the reals is this. Once I have a piece that factors into getting imaginary or complex zeros, then that's not factored over the reals anymore. So x minus 1, x minus 2, x squared plus 4. Now we want to factor it over the complex numbers. So we had just done that. We get plus or minus 2i, so that means that the factorization of this is x minus 1, x minus 2, x plus 2i, x minus 2i. So that's x minus negative 2i there, and x minus 2i. Oh, I missed that one. Okay, so here's the last one. This is giving us a formula, and we need to plug into it. It's pretty big. Let's take it over here. So before, when we were working with cubes, we talked about you just need to identify sort of what's A and what's B. So this tells us if we have x cubed plus some number times x equals some other number, then we can solve it this way. So we need to identify the numbers. So m is negative 9 because it's the number next to x, and n is 28 because it's the number on the other side of the equation. So x equals cube root of, I'm probably writing too big. Not going to be able to fit this on. x equals cube root of, and then there's a square root inside, n over 2 squared plus n over 3 cubed and then outside of that square root, n over 2, and then minus cube root of square root 28 over 2 squared plus minus 9 over 3 cubed minus 28 over 2. Okay, equals cube root of square root of 14 squared is 196. Minus 9 over 3 is negative 3. Cubed is negative 27. Plus 14. Minus cube root. Same stuff. But minus 14. So 196 minus 27 is 169. Okay, so that's the cube root of. Square root of 169 is 13. So this is 3 minus negative 1, so forth. Just to check, 4 cubed minus 9 times 4 equals 64 minus 36 equals 28. So way more complicated formula, but still really comes down to identifying two numbers and then plugging them in. You could have put this whole mess into your calculator once you knew the n and the n without doing it the way I did, the long way.